Hello, we are Group 12, also known as CEE Consulting, and our design project is the Broadway Bridge Barrier Gates. CEE Consulting includes Sam, our project manager and analyst, Sarah, our communication and CAD manager, Kang, our secretary and technician, myself, the QC manager and code consultant, and Majed, our information manager and researcher. The client for our project is Multnomah County's Bridge Department. Today we will be talking about the project background, the alternative analysis process we use to choose a preferred alternative, the facility design, and an in-depth look at the alternative that we chose, the conclusion, and recommendations for the next steps in the project. Our project is located on the Broadway Bridge. The Broadway Bridge was built in 1913 and is one of several bridges that spans the Willamette River in Portland. The bridge is located between the Fremont Bridge to its north and the Steel Bridge to its south. There's two sets of traffic gates located on the Broadway Bridge, one on the east approach and one on the west approach. Between the traffic gates and the bridge section that lifts are barrier gates. These barrier gates are our project, and we were tasked with redesigning them. The barrier gates themselves have a primary function and a secondary function. The primary function of the barrier gates is to stop a vehicle going any farther past the barrier gates while the bridge is lifted without doing serious harm to the occupants of the vehicle. And then the secondary function of the current barrier gates, as seen in this picture right here, is to act as part of the guardrailing while the bridge isn't lifted. Using the site location, we identified several possible stakeholders, and those stakeholders include the City of Portland, TriMets, Multnomah County employees and taxpayers, Portland commuters, and river traffic. Site conditions for our project are those typical of a bridge used by commuters. Approximately 30,000 vehicles per day travel across the bridge and is also used by pedestrians and bicyclists. The bridge is classified as a bascule lift and opens approximately 25 times a month to allow river traffic to pass below it. The streetcar, one of Portland's several streetcar lines, also runs along the bridge, and that includes the streetcar tracks on the deck and the overhead catenary system that hangs over the roadway. After our initial client meeting, our group decided to come up with a list of design requirements, and primarily we decided that the barrier gates needed to adhere to ASHTO safety standards. The gates must stop a vehicle that's traveling at approximately 30 miles per hour from going any farther past the barrier gates without doing serious harm to its occupants. The gates needed to open quickly and efficiently and should not interfere with the streetcar. And then any impact with the barrier gates should not transfer impact forces to the bridge frame itself. And this picture right here is kind of hard to see because of the lighting, but this is the current connection to the barrier gates that they're using right now, and it's connected through a hole in the bridge, one of the bridge members. And it's not an ideal connection because any impact to that barrier case is going to transfer most of the impact forces to the gate or to the bridge itself. Some of the design constraints that we identified for the project was the streetcar. This includes the streetcar tracks on the bridge deck and the overhead catenary system. These, both the tracks on the deck and the OCS lines have created unique challenges and have governed the design of our project. And another design constraint that we came up with later on in our project was the material of the bridge deck. It was found that because the type of material the bridge deck's constructed out of, any barrier gate design that uses a shallow foundation isn't going to be ideal and hard to implement. And now Kane's going to talk about the alternative analysis.
Right, thank you, Leah. So for the alternative analysis, our group have come up with 3 different designs. The first one is the pop-up bollard. So pop-up bollard is a short series of bolts hinged at the ground level, allow the pop-up bollard to be raised or lower from ground surface. Pop-up bollard could be operated through an electric or hydraulic operator. For the foundation, it depends on the length of the post. The second design we have is the GrabMat 300. also known as the ground retractable automobile barrier. As you can see here, the grab 300 consists of a steel anchor at the end here, 4 hydraulic absorber, and 1 cable assembly. Also the foundation for the grab 300, also shallow. The third design we have is the wedge. So wedge is a rectangular like platform barrier. So in order to stop oncoming traffic, the wedge could be raised to a 45-degree angle from the ground surface. Just like the other two, it could be operated through an electrical operator and also have shallow foundation. We also have an option of no build, but we'll talk about it later into our presentation. So after we talk with our client, we have come up with the 7 different criteria for our barriers. The first one is the vehicle damage, represent the inflicted damage from our barrier onto the vehicle. The second criteria is speed of operation, represent the time for the barrier to close or open. The foundation or connection represent the type or depth to connect our barrier onto the bridge. The fourth one is the gate mechanism, representing the mechanism our barrier going to use. The streetcar interaction represent the interference between our gate and the streetcar. And the sixth one is the aesthetic, represent the visual appearance of our barrier. Last one is the asphalt requirement, which is going to show if our barriers are going to be qualified for the asphalt standard. So as our group come up and discuss, we have our own system to rate our barriers. So from 1 to 5, if our barrier score 1 for each criteria, this means the least efficient. If score 5, that's the most efficient. So from out of 7 criteria, we see that vehicle damage, streetcar interaction, and asphalt approved. These 3 are the most important criteria that we're looking at. So let's say for vehicle damage, if the barrier score 1, that means that barrier is gonna cause the most damage onto the barrier, onto the vehicle. If score 5, that's the least efficient barrier and won't cause much damage onto the vehicle. For streetcar and asphalt, they're pretty similar. If they both score 1, that means they're not approved it. The barrier not approved it to get built. If score 5, that means they approve it to get built on the bridge. So with the build matrix, using the equation right here, we found that grab 300 is the best one to get built onto the bridge. So now Sam going to talk about our no design build.
Although the Pew matrix indicated that the grab 300 was the most efficient design for our gate, through continued talks with our client and through the Portland Bureau of Transportation, we learned that we could not affect the streetcar tracks in any way, or even build next to them or in between them. And this eliminated all the possibilities that we had except for the no-build option. And so with the help of Professor Christoph, we developed a modified swing gate design, and this would eliminate any barrier coming out of the gates, the track of the streetcar. And we designed this to ASTM M30 standards, which means it will be able to stop a 15,000-pound vehicle traveling at speeds up to 37.9 miles per hour. So we came up with this design and some modifications that we proposed with the client. Our first one was a cable net assembly similar to the grab 300 net, and this would be as a replacement to the stiff gate member that they have right now. And this would help with energy absorption. However, this would be a more complicated system and it'll be more expensive to construct. Our second modification proposed to the client was the addition of shock absorbers wherever the gate is connected to the bridge. And this would help absorb energy that will reduce damage that might occur to the bridge. However, this will be a more complex system and more expensive. Our third modification that we proposed was the supporting members. This would be adding supporting members that come off at 45 degrees from the main arm of the gate. And this would distribute the force to more parts of the frame instead of just 1 or 2. However, this would be more material and more moving parts for this gate to open or close. Our fourth modification suggested was the middle connection. So currently the gate comes out from both sides and doesn't quite meet in the middle. There's no actual connection there. And so we proposed that you would add a connector which would help distribute the force to both sides. However, this would take a solenoid to connect both sides. This is an expensive piece of equipment. And being in the middle of this road, it's very likely to be hit. So we proposed this design to our client and discussed with them which of these to eliminate, which of these modifications to eliminate. And we started with getting rid of the supporting members. The client decided that they would have to add more motors to the system, and that means more complexity and more things that can break and would be expensive to replace. And they also got rid of the middle connection idea because of that solenoid being right in harm's way would end up being a higher cost than just the efficiency it would provide. And they also added their own stipulation to our design, which was a single arm spanning the roadway instead of two that meet in the middle. And this would create a more simple design. However, this would be more load for one motor to take, and it would be more weight on the members supporting it. So this is, with our modified swing gate design with these three modifications in mind, we developed a new gate, which is a grab net similar to or it has a net system similar to the Grab 300. And here you can see a plan view of the gate spanning the entire roadway. This will be a net supported by an arm that's designed to break away. And so it's stiff to swing the gate all the way to the other side, but once it gets impacted, the majority of the force will be taken by the cables instead of a solid member. We also added shock absorbers to both sides that will reduce damage done to the gate. Now Sarah will talk about our design in more detail.
So our current proposed single-arm swing-out gate has a length of about 45.67 feet and a height of 3.33 feet. Also, the bottom of the gate is above the ground level by 1.4 feet. The gate is supported by a guardrail made up of three HSS 5x5 by half, which is supposed to keep the gate taut. This guardrail also tapers at the sides for it to decrease to only 2, which is the case throughout the bridge. The gate has cables of a diameter of about 5/8 inches, and those cables have an outer casing with a diameter of 2.8 inches. The suggested material for this outer casing, it could be made out of different types of materials, but after further research we found that the best two options were fiber reinforced plastic and aluminum. For fiber reinforced plastic, the photo here shows the fiberglass layer and the structural layer and the surface layer where the color is added. It's a good material because it's lightweight, it has a high mechanical strength, it's resistant to temperature and corrosion. It's also it has thermal insulation, it's easy to repair, cost effective, and most importantly, it's easy to mold, so it leaves a clean finish. The second material, which was aluminum, it's more cost effective and lighter than fiber reinforced plastic. However, the cost of aluminum has been increasing recently, and the difference between the price of aluminum and fiber reinforced plastic is not big enough to create that kind of gap. It also leaves an unclean finish, less durable and more costly to repair. Here's a diagram showing the aluminum foil, which is covered by a coating to prevent any damage, and the alloy where the color is at. After checking the ASH2 movable bridge manual, it referred us to the manual on uniform traffic control devices, and this is where we got most of our specifications from. So some of the specifications were that the gate should have an elevation of about 4 feet above the ground level. It should also have an array of red signals throughout the length of the cables. The cables should be colored in red and white, and anything else like the stanchion and piston, which are our shock absorbers, should be yellow. Our regulatory compliances and permitting includes agencies like the United States Coast Guard, and that's because they control the Willamette River as a form of shipping channel. Also, the Portland Bureau of Transportation needs to be informed in case there is any alterations, even if they're temporary or traffic closure on the bridge. Lastly, the Department of Environmental Quality, that's due to any leakage that could happen in the river. The resources that were used in our project were AutoCAD, SAP 2000, MathCAD, MUTCD, and the AISC Steel Construction Manual. AutoCAD was used for any visuals, also to locate where the connection would be on the bridge, SAP 2000 for simple modeling, MathCAD for most of the calculation, MUTCD for visual specifications and other specifications, but mainly that, and the AISC Steel Construction Manual for the selection of the swing outputs. Now Majed is going to talk to you more about what still needs to happen in the project.
Thanks, Sarah. In this section, I'm going to summarize the project background, resource design, and alternative analysis. Our main goal in this project is to redesign the barrier gate that is located in the Broadway Bridge. So, based on the selected criteria and the youth matrix that we did, our clear winner was the Graph 300. However, after communicating with the private company, they did not accept our design because they didn't want us to modify the streetcar trip. So in this case, we have to create a new design. And our new design is the swinging barrier gate. Opportunity analysis. We got the opportunity to use some of the classes that we taught in school into practice, such as steel design and structural classes and writing engineering. Also, some of us learn more on practice programs such as AutoCAD, MathCAD, SAP 2000, and Microsoft 2016. One of the main benefits that we get from this project is working with different agencies such as Multinational and Tribal. Also, we can get the skills of communication with each other and the client. Recommendation. The next step in this project is designing how the barrier gate is going to attach with the bridge. Also, choose what kind of materials to build the barrier gate, and designing the opening and the closing mechanism. After building the barrier gate, we recommend doing crash test. Right now, I'm going to show the crash test of the Graph 300. Yes. It's kind of expensive, but it's worth it to show if the barrier gate is going to work or not. Also, in this video, shows like why we recommended to use the Graph 300 instead of the regular barrier. It has less damage than the regular barrier gate. Thanks for listening, and any questions?
For clarification on the question, you mentioned that the motor resists the force below that gets applied from the car unit. So did I understand that's the motor and the gate doesn't actually swing out and lock into place with some sort of steel coupling?
Are you talking about our new design?
Yes. Yeah.
So it's designed to be, it's along one side of the bridge, and then a motor powers it to swing up, and then it'll be connected by probably a solenoid of the other side. Does that answer your question?
Yes.
Okay.
How often do people hit that gate, the current one?
They said very, not a lot, but
I think they have more people hitting it while it's not actually open than they do actually in its primary function.
Yeah.
How much was the whole estimate? You guys get a chance to do that?
Actually, we tried to communicate with the company that create the Graph 300, but they are not willing to share their data. This is why we didn't get the cost estimate for that.
Any more questions?
Thanks.